And this is version 2 of the review document. Should be the one I handed out. Okay, working from the same, singing from the same hymnal. All right, I've highlighted some, and we're going to start with number 5. Barium carbonate. Barium carbonate has a measured solubility of 4.03 times 10 to the minus 5 at 25 degrees. Determine the KSP. You have to assume that solubilities are in terms of molarity. Otherwise, we can't work the problem. So we're going to assume that 4.03 times 10 to the minus 5th molar is the solubility of barium carbonate. Barium carbonate. Barium is an alkali in the earth. Yes. 2 plus, 2 minus. That's our solid. And it's in equilibrium with its ions, cation, anion. Okay. And we're supposed to find out what the KSP is. Right. KSP, we would write the solubility product as barium concentration times carbonate concentration at equilibrium. There we go. So we've got our expression. We need values to go in that spot. So the solubility, they're saying, is um, 4.03 times 10 to the minus 5, which means that during this process, let's see. Oh, okay. We don't even have to do that. Here's the reason. Solubility says that's the concentration of barium, and that's the concentration of carbonate. So we just plug the values in. 4.03 times 10 to the minus 5 molar. And since they're both the same value, this is squared. So all you have to do is square that value. Did I lose anybody? Okay. 4.03 exponent and square it. So I get 1.62 times 10 to the minus 9th is the KSP. Okay. All right. That was pretty easy. If we can find a harder one. How about this one? This has got a good bit of algebra embedded. So the correct mathematical expression for finding the molar solubility of 10,2 hydroxide. Here's our solid. And it's an equilibrium. 10,2 means it's 2 plus. And then we have 2 hydroxide. Okay. We want the molar solubility. We know what the K is. Well, actually, okay. All right. So we've got an expression that's going to be equal to KSP. So since there's no value in here for the equilibrium expression, we need to pick something that tells us how many moles per liter of that goes in a solution. So we're going to pick S. The change is we're going to lose some of that. That's our solubility. So when we do that, one of these shows up over here, and two of those show up over here because of the chemical formula. All right, so we don't need anything here. We just need this. It's S, this is 2S, and we put those values into the expression for SN2 plus and, excuse me, I do OH minus squared. So now we can put our S's in there, which would be S here times 2S then squared. So when we resolve that, that's 2 squared is 4S squared, and the S squared times S is S cubed, 4S cubed. That should be equal to KSP, which looks like D. Right. Moving on. Number 11. Which of the following compounds has the lowest solubility in moles per liter, molarity in water at 25? All right, what we'll notice is that for each one of these, we don't have the same number of ions that are produced when they go into solution. Like first one, silver phosphate, produces 4 ions, or 3 silvers and 1 phosphate. One we were just looking at only produces 3 ions. So what that means is we cannot compare the KSPs directly. If they were all producing the same number of ions, then we could just compare the KSPs and answer the question. But the lowest solubility then requires that we do a calculation for each one. Cadmium sulfide, calcium sulfate, and aluminum hydroxide. Okay. All right. The KSPs, let's see. I'm just going to write this up here, KSPs, and put the values in there, and then we'll expand on that. 1.8 times 10 to the minus 18. 3 times 10 to the minus 27. 28. 6.1 times 10 minus 5. And 2 times 10 to the minus 3. All right. All right, so this is going to be silver to the 3rd power, because when it goes into solution, for each one of these, it produces 3 silvers. And it produces only 1 phosphate. Okay. This one is going to produce 110, 2 plus, and 2 hydroxyls. So that has to be squared. This one produces 1 of each. Cadmium 2 plus and sulfur 2 minus. And then calcium 2 plus and sulfate 2 minus. The last one, aluminum 3 plus. It's only 1 of those. There are 3 hydroxyl. Okay, so that should be our expression for each one of these without having to write out the equation. We know that that's squared, that's cubed, that's cubed. Okay, what we need to put in there is a value for solubility. Okay, So when this thing goes into solution, if we say that the solubility of each of these is represented by S, then that means when one of these goes into solution, you're going to get 3 of these. And that's going to be Q. Oops, and you get 1 of these. Okay? It should be square brackets. Okay? So following that trend, this is only going to produce 110, but it's going to produce 2 hydroxyls. That's squared. We follow that trend all the way down. This is an S, and this is an S. So it's 1 to 1. Same here. S and S. And this is going to produce 1 aluminum and 3 hydroxyl. And that's going to be Q. Okay. So we can resolve these into an expression like, let's see, this is going to be 3 times 27, right? 3 cubed, 27. 27 S to the 4th. This is going to be 4 S cubed. Okay. This is going to be S squared. This is S squared. And this is like that one. Okay. So now if we solve for S for each one of them, should let myself some room. Let's put it on this side. That's 11. We'll put it over here. This is the, actually, this is solubility. If we solve that equation. So for this one, we would divide that by 27 and take the 4th root of it. So we'll follow that pattern for each one. This is my Henry Ford assembly line. So 1.8 and exponent 15. And then we'll divide that by 27 and take the 4th root of it. So I need to go 0.25. Yeah. So in my calculator, I have to do 1/4 power instead of 4th root. Let's see. Here it is. All right. So I get a molar solubility of 1.6 times 10 to the minus 5th. This is molarity. Now I take 3, 7 there, divide by 4, and then that, and I get this one at 9.3 times 10 to the minus 10. And then I take minus 28, and I just take the square root of that one. This is 1 times 10 to the minus 14. And also take the square root of this one. Yeah. 7.8 times 10 to the minus 3rd. And the last one. Divide this by 27 and take the 4th root of it. And I get 2.9 times 10 to the minus 9th molar. Okay, so the question was the lowest solubility should be C. Cadmium sulfide is the lowest solubility. That was a lot of work. That's why I like to set it up as an assembly line. Then you think about what you're doing for each one and you repeat the process for every one. Then it becomes less laborious. Moving on, 13. Molar solubility of barium carbonate in 0.1 molar barium chloride solution. So we're trying to determine the solubility of barium carbonate in a solution that already has some barium in it. Right? The chloride is just spectator. So barium chloride, 0.1 molar barium chloride produces 0.1 molar barium ions. That's what we're dealing with. And the barium carbonate, we did this one before. Barium 2+, carbonate minus. Okay. So we have, if this is going to be the solubility, this is how much of that goes into solution. Then when we start off with 0 here, we end up with 1 barium, 1 carbonate. But that's not true. It's not 0. It's 0.1. So now we have a new set of values. This is S plus 0.10 and S there. So if we write the KSP, and the value is 1.6 times 10 to the minus 9th. And that's equal to, I'm going to jump over the those values and just put them in here. This should be S plus 0.10 times S. Okay. Now, here comes the possibility for estimating. Right? Is S a significant fraction of 0.1? Or is it going to be so small that we can ignore it? And I think we could probably ignore it. So that means this is approximately 0.10 times S. And then we can solve for S as this divided by 0.1, which is 1.6 times 10 to the minus 8. Divide by 10 to the minus 1, it's like adding power of 10. So, did I come close? Or I go the wrong direction? So it needs to go in. Oh, I did go the wrong direction. Because, okay, that's what I get for skipping steps. 1.6 times 10 to the minus 9 divided by 10 to the minus 1. Well, that should be right. Oh, none of these. Yeah. Okay. Yeah, I got it right. 1.6 times 10 to the minus 8 molar. And that's not in our list. Yeah. Probably the most likely answer that I'll get that's wrong is A. Okay, 17. Okay, which of the following solid salts is more soluble in 1 molar hydrochloric acid? Well, not hydrochloric, just 1 molar H plus. Right, we would pick our hydrogen vehicle in such a way that the anion would not interfere with the reaction. It would be a spectator. But if we manage to put our solid in a solution that is 1 molar in hydrogen ions, remember you have 2 ways to solubilize a slightly soluble salt. One is if you have the, let's do it this way. you have the cation and the anion, and those can be different charges. If you use an acid to solubilize this salt, what you need, this is a solid. So we would have that plus this. What you need is something to remove this from solution, right? So what that means is this has to be a very strong base. It has to love hydrogen ions. So if this were the acid, this would be a weak acid. This would be a weak acid, which means it wants to be back this direction, right? When it produces those ions. So that means if it prefers this side, when you put that in there, it's going to latch onto that and drive it back this way. So by adding hydrogen ions, you are producing that and shifting the equilibrium this direction. Okay. So which one favors that? Well, if we look at the first one, sodium chloride, the chloride ion is very weak base because hydrochloric acid is a strong acid. Same thing for potassium chloride. How about potassium nitrate? Well, the nitrate would be derived from nitric acid, which is a strong acid. That makes nitrate a weak base. So it doesn't work. Silver chloride, right? Chloride is the product of a strong acid, so it's a weak base. Calcium carbonate. Calcium carbonate produces this plus this. That is a very strong base because carbonic acid is very weak. That makes this a strong base. So you go for B, calcium carbonate. This would solubilize calcium carbonate. And not only that, if you add these hydrogen ions to calcium carbonate, you're going to get a lot of gas too. But that's a secondary reaction from the combination of like that. Then this decomposes into water and CO2. So that's where the fizzing comes from. But the reaction that we're interested in is this one. That's secondary. It's 17. Let's see. 19. You have a solution consisting of 0.1 molar chloride and 0.1 molar chromate, and you add 0.1 molar silver nitrate dropwise to the solution. Given that the KSP for silver chromate is 9 times 10 to the minus 12, and for silver chloride is 1.6 times 10 to the minus 10, which of the following will precipitate first? Okay. What we have to do is look at the solubility. So we have two different reactions here. We've got silver and let's see, we've got chloride ions in solution, and we're adding silver dropwise as silver nitrate. So we're starting off with chloride, and we're going to produce silver chloride solid from this reaction. Okay. And the other one we're going to produce is silver chromate. Solid produces two silvers plus chromate. Oops. This is aqueous and this is aqueous. Okay. So for this one, our KSP is going to be equal to silver concentration times chloride ion concentration. And this one, our KSP, is going to be equal to silver squared times chromate squared. Okay. Which one has the, what's the solubility with 0.1 molar silver nitrate? Let's see, am I approaching that right? Because we're adding this dropwise. I'm thinking about how I worked it out here, and maybe there might be a better way. Which of the following will precipitate first? All right. Well, the one that precipitates first is the one that's least soluble. Yeah. Right. So we just need to calculate the solubility. Let me put the values up here. 1.6 10 to the minus 10 is this one. Notice I put them in there backwards. And 9 times 10 to the minus 12. There. Okay, so what's the molar solubility? As we add silver to this, we're going to find out what the solubility is. So we're going to, the solubility here is we're going to lose some of this. I start off here and here. We're going to gain one of these and one of these. So we have S and S total. That means this is going to be equal to S squared. Right? S here and S here. This one, on the other hand, is going to be its solubility will be a different S, of course. I'll put this there like that. There we go. This is going to produce two S's, and this is going to produce one S. Yeah. So we get two S's here and an S, and this expression is going to be equal to, I have to put it up here. It's going to be 2S in here squared. So that's 4S squared times S is 4S cubed. Okay. So now we can calculate the solubilities. So 1.6 minus 10, and just take the square root of it. So this S here, S is equal to 1.3 times 10 to the minus 5 molar. And this one is 9, 12. This one we divide by 4 and then take the cube root of it. That's equal to 1.3 times 10 to the minus 4. Okay. So which one precipitates first? Silver chloride. It's the least soluble by an order of magnitude. I think that's the way I solved it. More problems. I couldn't think of a better way. I was looking for shortcuts, but none came to mind. All right, 21. How many moles of calcium nitrate must be added to 1 liter of 0.182 molar KF solution to begin precipitation? All right, when does precipitation begin? It begins when the Q exceeds the KSP. So what we want to do is calculate the Q for this system, right? I think that's what I want to do. Yeah. We're going to set up a situation where the Q and the KSP are equal. And that's when precipitation starts. So calcium fluoride is the ultimate solid that we're looking at. Calcium fluoride solid. I used to have you've heard me talk about my inductively coupled argon plasma spectrometer. One of the lenses in the lens, focusing lens in that system was calcium fluoride. It's very soft and fragile. So when you clean it, you have to be really careful. But calcium fluoride was used as the lens because it transmits ultraviolet radiation. And some of the wavelengths that we're interested in capturing from our elements in the analysis are in the ultraviolet range. We couldn't use quartz because it would absorb all the UV. So we use calcium fluoride. Okay, this is calcium 2 plus and 2 fluorides. Okay, what else do we know? We know the KSP is 4 times 10 to the minus 11. Okay, and that will be equal to calcium 2 plus and whatever the fluoride is squared. Okay, so what are we starting out with? What's the change and what's the equilibrium situation? All right, this solubility is going to be, we're going to lose one of these and we're going to show up with one of those and 2 of these. But we have conditions up here that are going to change because the fluoride concentration is already known at 0.182. Okay. So now we have S and we have 2S plus 0.182. I think that's where I think I'm going right there. Now I'm approaching it wrong. Let's back up. Precipitating calcium fluoride. I don't know, this might work. If these are the starting conditions, 0.182 fluoride, yeah. Okay. I see where we're headed. We're going to add calcium to this system. So it's not really an ice equation. We're going to add some calcium to this system, and it's going to consume the fluoride. Right? So if we start off with this, and then we add some calcium, it's going to pick up two of these, and that's going to be the equilibrium situation for our Q and our KSP. Let's see, does that make sense? Yeah. Because we want to know what the calcium concentration is. We don't care about this. Well, we do care about solubility insofar as this expression feeds into the solubility. But we're looking for the Q that's equal to KSP, equal Q. So now if we put those in to our expression, 2s minus 0.182 squared. And this is 4 times 10 to the minus 11. And we're still going to say that this is so small, it doesn't matter. So this is our S, and this is going to be 0.182 squared. You know, it would have worked the other way too. Because you square a negative, you get a positive. If we'd left that positive, it'd still be a positive squared. So it just would have been the wrong concept. Okay, so here's the equation we have to solve. We're going to square this, divide it into that, and that's our S. But that is, that doesn't answer the question though. How many moles of calcium nitrate? This is the molar concentration. Okay, so we're only part of the way there when we solve this equation. 0.182 squared and divided into 4, 10 to the minus 11. So I get 3.96 times 10 to the minus 3 molar is the added calcium. And if it's 1 liter, and we have to assume that we didn't change the volume that much. So for 1 liter, this molarity times volume equals moles times 1 liter. So that's 3. Actually, it's closer to 4. Now, why is it 1.2 times 10 minus 9? I did something wrong. I did. My calculations are wrong. Let me do it again. 182 squared. Yeah, squared. Garbage in, garbage out. So that times 1 liter is 1.2 times 10 to the minus 9 moles. Right answer. Okay, that was kind of tricky. Because we were actually working backwards. At what point does adding enough of this make that? All right, 23. Am I going to run out of time? How much time do I have? Oh, okay. Well, we might make it if I don't dawdle. A solution of 0.01 molar in each of lead, manganese, and zinc And solid sodium hydroxide is added until the pH of the solution is 8.5. Which of the following statements is true? So we're talking about precipitating these metals as the hydroxides. All right. So we've got lead hydroxide, lead 2 hydroxide. We've got manganese 2 hydroxide, zinc. Yeah. And this produces lead 2 plus, manganese 2 plus, zinc plus. Actually, we're going backwards. And those are aqueous. These are solid, that's aqueous. Okay. If we know, well, let's do one of them because they're each going to end up with the same expressions for the KSP. Okay, so let's just do one of them. If we're starting off with a pH of 8.5, what we want to know is what's that concentration. So POH equals 14 minus 8.50. So that's 5 and 8/13. Right. Yep, that's right. That's POH. OH is equal to 10 to the minus 5.50. So this is 3.16 times 10 to the minus 6 molar hydroxide concentration. So this is where we're starting at 3.16 times 10 to the minus 6 molar. All right, if we bring this down, and we want to know what is the second guessing myself. I was starting to make it more difficult than it is. What's the Q here? Well, if we have that concentration there, and we have let's see, 0.01 molar in each one of these. 0.01 molar, 0.01 molar. So if actually that's not right. We have 0.01 molar in this because each one of these is made from the nitrate. Yeah. So now we can calculate the Q for each one. So what's the Q going to be? Well, Q is going to be what's the lead concentration and what's the hydroxide concentration squared. Okay. So 0.01 times 3.16 times 10 to the minus 6 squared. Actually, that's going to be the Q for each one of them. So I already got that one in my calculator. I'm going to square it. And then 0.01 times that. So the Q is 1 times 10 to the minus 13. All we have to do now is compare the Q to each one of these KSPs. Oh, I didn't write them up there. All right. KSP for this one is 1.4 times 10 to the minus 20. Right? Q is greater than 10 to the minus 20. It's going to precipitate. KSP for this one is 10 to the minus 13. 13. And that's less than. That's about half of this value. So no precipitate. And the last one is 10 to the minus 16. 16. Okay. That is greater than this. This will precipitate. Let's see. Oh, I put those in the wrong place. This will precipitate. This will not precipitate. This will precipitate. So lead and zinc will precipitate. Only zinc and lead will precipitate as D. Okay. All right, 24. Oh, we use our table. Selected precipitation table. So, how are the analytical group 2 separated from cations of 3 through 5? So 2 separated from versus 3 through 5. So let's scroll down and see how we separate 2 from 3. We're getting warm. Okay, there's group 1. And all right, so we're going to separate 2 from 3 through 5. The solutions here, I don't know if you can see that, 3 through 5 are left over after we add hydrogen sulfide. And we add hydrogen sulfide in acidic solution. Okay, we haven't added base yet. This is acidic solution, so that means the concentration of sulfide is very low. All right, so we'll go back to 24. And hydrogen sulfide in acidic solution forming insoluble metal sulfides is C. That was simple enough. Hydrogen sulfide in acidic solution. We'll separate that group from the others. All right. 25. Which of the following solid salts should be more soluble in 1 molar ammonia than water? So you got a solution of 1 molar ammonia that we're trying to use to solubilize these salts. Actually, this is a pretty simple question because the only one we've studied so far that solubilizes with ammonia is silver. So silver bromide is the answer. The reason it's the answer is that when you add ammonia as a ligand, you're attacking the cation. Right? And if you're attacking the cation, you got to have something that will bond with ammonia. Sodium won't do it, potassium won't do it. Silver is the only one that'll do it. That's almost a pure memorization problem. 27. Looks like we're going backwards. The correct mathematical expression for finding the molar solubility of lead-2 chloride. Okay. This would produce that aqueous plus 2 chlorides, which means the KSP expression would be a single S for that one and a 2S for this one because it produces 2 for every one. In addition, it's squared. Right? So this would be 4S cubed. Would be D. Okay. 30. Probably should have had this one earlier. Which of the following leads to the formation of precipitate when the Q exceeds the KSP? That's C. Calculate the solubility of silver chromate in a 0.049 molar silver nitrate solution. All right, we did one like this before, but practice makes perfect. I think that's right. Yep. And this will produce 2 silver, 1 chromate. Okay. And we're starting off with 0.049 silver, 0.049 molar, and none of that. So that's the initial conditions, change and equilibrium. So for calculate the solubility, the molar solubility, we're talking about putting this solid in solution. So we're going to lose some of that, and it's going to show up as 2 of them over here and 1 of these. So our expression then would be 2S plus 0.049 S. So the KSP is 9 times 10 to the minus 12. 9 times 10 to the minus 12 is equal to this one squared because of that. 2S plus 0.049 squared times, and the solubility is relatively low. I mean, we can't tell exactly from that, but we can infer that with this very small number, that value is going to be is not going to be a significant fraction of this one. So we're going to say that that's approximately 0.049 squared times S. And we're going to solve for S. So that means we square this value and divide it into that one. I get 3.7 times 10 to the minus 9 molar. Okay. All right. 36 coming up. Yeah, 36. Okay. Second against myself again. So this is almost like the one we did before. How many moles of calcium fluoride will dissolve in 3 liters of 0.049 sodium fluoride solution? All right, the common ion here is fluoride. And if it's already in solution, it's going to inhibit the dissolution of calcium fluoride, which means it's going to decrease its solubility from what it would be in pure water. Okay. So we got the solubility again. How much of that will go into solution and produce one of these and two of these? But we're starting off with 0.089 fluoride, 0.089 molar fluoride, and no calcium. So we get sulfur 0.089 plus 2S. And then we can fit that in our equation. If we know what KSP is, which is 4 times 10 to the minus 11. And that's equal to, that's going to be S for the calcium and 0.089 plus 2S squared for the fluoride. And again, we're going to approximate. So this is S, and this is 2S squared. So that's equal to 4S cubed. Oh, excuse me. You big dummy. Sanford and Son. Yeah, we're taking that one to 0. And this is our equation. Times 10 to the minus 11. And this would be, over here would be 0.089 squared. This would be 7.92 times 10 to the minus 3. And that's equal to S. That's 1. Can that be right? Let me try that again. 4, 11, 0.089 squared, divided into that. No, that didn't look right. 5 times 10 to the minus 9th molar. We're not answering the question yet. In 3 liters, how many moles of calcium fluoride? So if we know the solubility of this in terms of molarity, then times 3 liters will give us the number of moles. Remember, molarity times volume equals moles. That's 1.5 times 10 to the minus 8 moles of calcium. Ten to the minus 8. C. Here it is, C. Okay. Set that aside. All right, 37. What's the best way to ensure complete precipitation of tin 2 sulfide from a saturated H2S solution? All right. If you want to, we don't even have to go to the chart. If you want to be sure that you get all of the tin removed and there's nothing in there but tin, then you need to flood the system with sulfide. And the way to do that, because you've got an equilibrium here with 2 hydrogens and 1 sulfide. If you, in order to flood the system with sulfide so that you can precipitate all the tin, you need to drive the reaction as far to the right as possible. So what we do is add base. Hydroxyl is extremely strong base. It's about the strongest one we know of in terms of Bronsted-Lowry base. And that drives it over here to that. So that produces all the sulfide you're going to need to precipitate all the 10. And that would be D, add a strong base. Now we could add some other base in there, but this is the best one. A strong base. I guess we could add carbonate, but that would mess things up because it would, well, maybe not. What would happen if we added carbonate there? That would remove the hydrogens and produce CO2. So when it produces CO2, it removes it from the solution and it keeps driving the reaction. That might work, you know, if you didn't have any hydroxide around. Bubble carbon dioxide through it. Okay, I'm just speculating. All right, number 40. Okay. The concentration of magnesium 2+ in seawater is 0.052 molar. At what pH will 99% of the magnesium be precipitated as the hydroxide? Okay, we want to precipitate not all of it, 0.052 molar. We want to precipitate 0.99 of that. So the magnesium that we want to remove is equal to 0.99, the decimal equivalent of 99%, times 0.052 molar. Okay. That's 5.148. I'm going to keep a decimal, so we reduce possibility of rounding error. So that's actually what we want to remove from solution. Okay. So if we're going to precipitate that as the hydroxide, then we're looking at the equilibrium here of this solid with these ions. And the KSP for magnesium hydroxide is 8.9 times 10 to the minus 12. 8.9 times 10 to the minus 12. And that's equal to magnesium concentration that we want to remove, which is this one. 5.148 times 10 to the minus 2 times hydroxides, right? That's our unknown. Yeah, that's our unknown. There we go. So we've solved for the hydroxide, and the question, look back at the question, at what pH? So if we can find out what the hydroxide ion concentration is, we can calculate pH. All right, so we're going to have to divide this one by that one. 8.9, 10 to the minus 12, and then 5.148 10 to the minus 2. And that's 1.729 times 10 to the minus 10 equals hydroxide squared. So the hydroxide concentration is going to be the square root of that value. 1.31 times 10 to the minus 5 molar. So the POH is a negative log of that value. which is, let's see, I really only was allowed 2 here. So I've got 4.88 POH. And pH is equal to 14 minus 9.12. Okay. All right, let's see, 41. All right, a solution containing 0.01 moles each of iodine, bromine, chloride ions. When the solution is mixed with 200 milliliters of 0.24 silver nitrate, how much silver chloride precipitates out? All right. So, all right. The KSPs for each one, and then we start off at the top with silver iodide. And the reason we put them in this order, and the reason they're in this order in the problem is because each one of these produces the same number of cations and anions. So we can compare their solubility based upon their KSP, right? If we calculated the solubility, we get a comparison, but it'd be exactly the same comparison as the KSPs. So when we say the KSP here is 10 to the minus 16, 10 to the minus, was it 13? Yeah, 13. And 10 to the minus 10. That means that of all of that silver that's put into solution, this is going to get, we're going to make silver iodide first. So with 0.018 moles of each one of these, 0.018 moles of each one of these, and that means 0.018 moles of chloride, bromide, iodide. With 200 milliliters of 0.24, 200 milliliters of 0.24 molar silver nitrate. Right? Yep. How much silver are we starting with? Well, volume in liters times molarity is moles. So this would be 0.2 liters times 0.24. That's how much silver we're starting with. And the reason we're going that route is because the question is silver chloride precipitate at the end. We're going to do these in sequence, right? We're going to use up all the iodide first, more than likely. 0.2 times 0.24 is 0.048 moles of silver. Okay? That's what we start with. So if we start with 0.048 moles of silver, and we're going to use it up in a one-to-one relationship here, then we just subtract 0.018, and this gives us our starting point for the next precipitation. So that's 0.03 moles of silver. Okay, Then we subtract this amount. 8 is 2, right? Yeah, that's right. And this is what we've got to start with the next one. Well, it's a one-to-one relationship, right? So this is excess and this is limiting. So all of that's going to be used up. That means this is how much silver is going to be converted into silver chloride. All right. So the question is, well, we look at the answers. The answers are in grams. So we got to convert this, which is the same as 0.012 moles of silver chloride because of their one-to-one relationship. Now we can just convert this to silver chloride. We need the molar mass of silver chloride. So silver is 107.87. Chloride is 35.45. So that's 143.32. Yep, grams per mole. 143.32. So that should give us our answer. How many grams of silver chloride? And let's see, how many? Two significant figures. 1.7 grams of silver chloride will be produced at the end. Oh, we got another. Selective precipitation. My guess is that our list of selective precipitations is a starting point. And then there are, it's like a tree, branches to separate, like group 2, you would have a certain mix of the, and you go in and use a different wet chemistry procedure, separate some more of them. Eventually you get down to separating all the ions, all the metal ions from each other. So what are we looking for here? Containing cations of analytical groups 1 through 3. So we're starting with 1 through 3. Right? We're not starting with the whole shebang. Treated with H2S in acidic solution, which cations are expected to precipitate? All right, so let's go down and look at it just to be certain. Let's see. Yep. In acidic acidic H2S, we want the least soluble sulfides. Okay. There's where we add, there's the acidics. And this is group, was it group 1? Solutions 1 through 3. 1 through 3, okay. So we don't have the barium, calcium, or magnesium. That's the only difference. And we want to add acidic H2S. If we add hydrochloric acid, we're going to take out silver, mercury, and lead. H2S is going to take out copper, bismuth, cadmium, lead. Okay. So let's go back up. 43. Which cations are expected to precipitate? If we acidify and add H2S without going through the separate step of acidifying, then we're going to get both 1 and 2 together. That's the point that's being made here. If you do it stepwise and acidify first and get those precipitates out, then you can get group 2 by itself. But if you just acidify H2S in that solution, then you're going to get 1 and 2 together. So that's why D is the answer. All right. This one is a challenge. Number 46. We'll put this way up here so I have plenty of room. Oh no, this is not the one. I was thinking of another one. This one's fairly straightforward. Cation M2 plus reacts with ammonia to form a series of complex ions. So this particular metal forms a triamine. And notice that the K values for each one of these processes, the K is very large. The first one is 100, the second one's 1,000, the last one's 100. So what you can assume is that the procedure is effectively going to completion for each one of those steps, which means the final value is completion. And if we combine all of those together and we get this equation, so M2 plus 3 ammonias yields ammonia 3 and 2 plus in solution. Okay, so what's the K for that one? The K for that one is K1 times K2 times K3. Okay, the question is, what's the dominant species? All that other stuff at the bottom might be necessary for solving actual concentrations. And I think I put that in here as just a teaser. But to answer the question, if we put these together, 2, 3, and 2, and 2, 3, 2. That's going to be for 12. 10 to the 12th is the overall K. That means that it's going all the way to that one. So the dominant species is the final product, D, the triamine metal. Now, that's not to say there won't be a little bit of the intermediates left over, sitting out there, but there won't be much of them. 47. All right. This is the one that had me quaking in my boots. I think. No. This one shouldn't be too bad. Yeah, this one shouldn't be too bad. What's the concentration of nickel 2 plus ion in 0.045 molar nickel nitrate solution that is also 1 molar in ammonia? So what we're saying is, what's the leftover nickel concentration in solution? Yeah. Okay. So the equilibrium we're looking at here is a complex ion equilibrium. And we know that we've got a concentration for nickel ions to start with, and we have a concentration of ammonia to start with. And the Kf, the formation constant, tells us what the complex ion is, right? It's a hexaamine nickel 2 plus. If you go to that handout I gave you and name it correctly. So we're looking at nickel in solution plus 6 ammonias in solution is in equilibrium with this complex ion. There we go. And the KF, I'm going to write it up here. The KF is 5.5 times 10 to the 8th. There we go. All right. So the best way to handle this one is like we did in previous chapters, where we did stoichiometry first, and then we let the equilibrium take over. So the stoichiometry here has 0.045 molar nickel. 0.045 molar nickel. This is initial, so what's left over final. And 1 molar ammonia. Right, okay. So what's left up? What we're going to do here is we're going to use up all the nickel. So the final concentration is 0. And for every 1 nickel, you have 6 ammonias. So what we need is 6 times 0.045 is what was used up of the ammonia. And it's going to produce 0.045. Let's see. Initial is 0. Final is 0.045 molar in that compound. And this one's going to be 0.045. 6 is 0.270. Oh, excuse me. 0.270 subtracted from 1. So this is going to be 0.730 molar. Okay, now we have our starting point, our initial concentrations for an ice table. Okay, so we're going to start off here with, this is going to be 0. This is going to be 0.730. This is going to be 0.45. Okay. And then we're going to have a change in an equilibrium. Okay. All right. So which way is it going to move, this equilibrium? Are any of the values 0? Yeah, that one right there. That means it has to move this way. So we're going to add a certain amount here. And since we're not talking solubility, I'm going to have to use X. So we're going to add some X here. And that means in order to do that, we've got to lose an X over here. Right? So this is 0.450 minus X. So what is this one? Well, if that one's a minus X, then we're going to shift them this way. We're going to add 6 X's here. Right? Okay. So 0.730 plus 6X. All right. So that's part of our equilibrium expression. Let's see. I'm still on the right track. Yeah. Okay. All right. So what's our KF expression here? Well, it's going to be the complex ion. This is equal to the complex ion equilibrium expression. Nickel and ammonia, 6 times that one, 2 plus. In the numerator, and in the denominator, we have nickel 2 plus, and we have 0.730 plus 6x to the 6th power because of that. Okay. Oh. I'm mixing apples and oranges. All right. This is going to be the ammonia. This one's going to be X for that one. And this one's going to be 0.45. 0.545 minus X. So there's our expression. All right, how are we going to deal with that? Well, hopefully we can, since this value is 10 to the 8th, it's going to be mostly over here. Okay. So if it's mostly over there, we're not going to be able to subtract very much X. We're not going to add much X over here either. So the X's tend to fall out. That means this is going to be 0.450. This is still going to be X because we got to have an X somewhere. We can't solve the equation. And then 0.730 to the 6th. And that's all equal to 5.5 times 10 to the 8th. Okay? All right. If we put the X over here and replace it with this one over here, then we can find out what X is. So I'm going to say 0.45 in the numerator, then 0.73 to the 6th power. Yep. And divide that into this value. And then divide everything by 5.5 in the 8th. And that should be equal to X, or the concentration of nickel. 5.4 times 10 to the minus 9th molar. Oops. Okay. Did I make a mistake somewhere? 0.45. Oh. Is that wrong? Well, I erased everything now. All right. 0.045. This should be 0.045. There we go. This should be 0.05. There we go. Oops, here also. Well, let's try that again. 0.045. Oh, it's just going to move the decimal to one more negative. Yeah. Right, because we reduced this one by 1/10. That changes this one 10 to the minus 10. So A is the answer. I ought to go back into my videos and compile bloopers and then make a quiz out of it and see if students can catch the error before I do. It's got to be some way to save face. That's why I use the key. Okay, Kf for the complex ion. Diamine silver 1 is 1.7 times 10 to the 7th in this problem. I think in your the accepted value in there is 1.6, I believe. Anyway, the KSP is 1.6 times 10 to the minus 10. Calculate the molar solubility of silver chloride in 1 molar ammonia. All right, so we've got two equations operating here. One is the formation, and it's all happening in the solution at the same time. So we've got solubility of silver chloride. Silver chloride solubility, silver plus chloride. And we've also got, we'll move it down here just in case I need space. We've also got the formation of the complex ion. Oops, not two ammonia. Remember, has to be ammonia. Ammonium won't work. And this forms the complex ion. 2 and plus. Okay. If we want to find the molar solubility of silver chloride, the best way, the easiest way to do it is combine these equations. And we've got a KSP of 1.6 times 10 to the minus 10. KSP equals 1.6 times 10 to the minus 10. And this is KF equals 1.7 times 10 to the 7. So if we combine these equations, which we can do, according to Hess anyway, we would get silver chloride solid. And here we would get silver and 2 ammonias. And on this side, we get silver. And we get chloride. And we get the complex ion. And then the equilibrium constant here would be that one times that one. I think I'm marking up the right 3. Okay. Let's see. Yeah. 1.6 10 to the minus 10 and 1.77. And that's 2.72 times 10 to the minus 3. Okay. We can cancel common ions, right? The silver drops out. Let's see. Let's look at the question. Calculate the molar solubility. All right. We can't, if we cancel the silver, we can't solve the problem in terms of silver ions, but the solubility is also 1 to 1 to 1 for chloride. So we can make chloride our unknown. So this silver drops out. And the KEQ equals chloride. Probably seen this equation before. And the complex ion, right, divided by silver chloride drops out. I mean, it's not part of the expression. And then ammonia squared. Okay. So if we set up our ice table, see. Am I barking at the wrong tree? Yeah. Let's see if I've got everything right. Okay. So the solubility now is going to be in terms of how much of this can we produce? Right. If we say the solubility here is in terms of S for that one, it's going to produce, let's see, if we start off with 1 molar ammonia. 1 molar ammonia. And that's it. 0 here and 0 here. Then this is going, we're going to produce this much chloride. And we're going to lose 2 of these ammonias for every chloride because the chloride and the silvers are 1 to 1. Okay. And then we're going to also produce one of these. All right. Okay. So that means 1 minus 2s, and this is s, and this is s. Okay. So if we plug those values in here and use our 2.72 times 10 to the minus 3 equals, and then chloride is S, and the complex ion is S. And then in the denominator, we have 1.0 minus 2S squared. Okay? Well, that top term is squared also, isn't it? Okay? So this is nice because if we take the square root of both sides, we can get rid of that square. So if we take the square root of this one, we get S over 1 minus 2S. And the square root of 2.72 10 to the minus third is 5.22 times 10 to the minus 2. Yeah. So now we got to do some more algebra. This one times that one. 5.52 times 10 to the minus 2 minus 2 times that. 1.04 times 10 to the minus 1 S equals S. Right? And say 1 times this one minus 2 times that one S equals S. So now I got to get the S's on the same side. 552 times 10 to the minus 2 equals, this is minus here, so it's a plus on that side. This is 0.104. So it's 1.104 S. And then S is this value divided by 1.104. Let's see, 5.52 divided. So I get, is that right? 5 times 10 to the minus 2 molar. Close. Now, why is it only 4.7 there? I must have made a math error somewhere. I either made a math error there. 272 10 minus 3 is correct. 522. That's correct. 2. Let's see if I did that. 5.22 exponent Enter 1.104 divide. Oh, I did make a mistake. This is 4.7. Math error. It gets you every time. Okay. And let's see. Here's the one that gives me nightmares. 52. I'm very, very methodical about this one. All right, for the system, 500 milliliters of 0.02 molar manganese nitrate. So that's 0.02 molar manganese, nitrate's a spectator, mixed with 1 liter of 1 molar sodium oxalate. C2O4 is the anion. Sodium's another spectator. Sodium and nitrate are spectators in this reaction. The oxalate ion acts as a ligand to form a complex ion with the manganese ion with a coordination number of 2, which means manganese plus 2 oxalates yields the complex ion. Only notice that that second equation, complex ion's on the wrong side for our purposes. What's the equilibrium concentration of the intermediate MnC2O4? All right. If we're going to calculate the, well, let's put the reactions up here first. Mn and the oxalate. C2O4. This is the one we're after. No, not this one. The other, this one right here. C2O4. And notice the charge is balanced, so this is a neutral compound. But it is in aqueous solution. And the K is 10 to the third. Well, it goes way over to the side. And then the second equation, though, is written backwards. So what we need to do is reverse that equation in order to write the overall equation. Because the overall equation is going to determine our starting point for the reverse. We're going to do the stoichiometry of the overall equation. Yeah. So instead of putting that up there, I'm going to write it in reverse now. So we'll take that one, Mn oxalate, plus another oxalate. And that produces this final complex ion. So what's the K for this one? Well, the K for this one is the inverse of the K2 that's given to us because we flipped the equation. So I just need to take the inverse of 1.26. Let me write it that way. 1.26 times 10 to the minus 2. Invert. So this is 7.94 times 10 to the first power. What that means is that most of it is going to end up as this. And only very small amounts can be left as that. And then the overall for the reaction. Let's see, are we going to need that? Yeah. Well, we may not need that. Because, yeah, we are. We're going to have to add these two together. So we've got manganese plus two of these. Yields complex ion, the final version, C2O4 minus this. And that's because that one cancels and that one cancels. And the equilibrium constant is we may or may not need it. I'm going to go ahead and calculate it just in case. The equilibrium constant for this reaction is that one times that one. 7.9, 3, and 7.94. So this is 6.27 times 10 to the 5th. All right. So now let's, what are the conditions? 500 milliliters of 0.02 molar manganese. So we got 500 milliliters, 0.02 molar manganese. And 1 liter of 1 molar of that. So we got 1 liter of 1 molar of that. Okay. So when we put them together, what's their concentration? Well, we've got a half a liter here. So if we change that to liters, 0.5 liters, then 0.02 times 0.5 is 1 times 10 to the minus 2 moles. But what's the new volume? 1.5 liters. So our new concentration is 6.67 times 10 to the minus 3 molar. And this one gives us 1 mole divided by 1.5 liter. And that's equal to just the inverse. Is 6.67 times 10 to the minus 1 molar of that. That's what we're given to start with. So I think what we have to do first is say, what's the stoichiometry first? Right? So this is going to be excess, this is going to be limiting. So if all the manganese, if this is the initial concentration, then the final concentration is going to be 0 here. It's going to be this one minus 6.67 times 10 to the minus 3. Which is 6.60 times 10 to the minus 1. And it's going to produce one of these. So it's going to produce exactly 6.67 times 10 to the minus 3 molar of the complex ion. So this is where we start our equilibrium. Now we can work backwards. All right. This is the manganese, the oxalate, and the final, and this one. So we have this one here, right here. We have this one here, and we have nothing there. So let's see. Kind of ran out of room, didn't I? Let's see if I can squeeze it in here. Because what we want is to use, we want to find out what this concentration is, which will be the same as that one. Right? Because it's all mixed in there together. We can find out what this is. So what we need is our K2 to the minus 1 is equal to 7.94 times 10 to the first. And that's equal to this intermediate complex ion. No, this is the final, excuse me, the final complex ion, right? Divided by this intermediate complex ion times the oxalate. There we go. So that's what we're after right here. We want to solve for this one. So if this is moving back this way, because that's 0, it's moving back this way, then it's going to give us an X value. Right? We're going to have some of this from this reaction. And this is 1-to-1 ratio. So this is going to be 6 minus 6.67 times 10 to the minus 3 minus X. This is also going to produce one of these. For every one of these, we strip off one of those. So this is also a plus X, but it's starting as 6.60 times 10 to the minus 1. So there are our values for the equilibrium, these right here. So 7.94 times 10 to the first is equal to 6.67 times 10 to the minus 3 minus X. And then on this side, we have X. And this is 6.60 times 10 to the minus 1 plus X. Okay. Now, is X going to be a problem? I don't think so. I think X is going to be so small because the reaction is essentially all the way to this end. So very little of that is going to be reconverted into this as we work backwards. So I think we can say this is approximately 6.67 times 10 to the minus 3. Drop out the X. This is over X times 6.60 times 10 to the minus 1. And that's how we solve for this one. We bring these two over times that value, and that's equal to this value. I'm going to have to make room now. Okay, so this term right here times that term. 7.94 exponent 1 times 6.6 exponent minus 1. This becomes 5.524 times 10 to the first power X equals 6.67 times 10 to the minus 3. Now X is simply this number divided by that number. And I get 1.27 times 10 to the minus 4 molar for this intermediate. Okay, 1.3. They rounded off 2, which is proper. I think I only had 2 significant figures anyway. Okay. That's a bear. Okay. So now we're down to 53. Across the home. Yeah, this one should be easier. What's the molar solubility of lead 2 chromate in 0.055 molar sodium thiosulfate? Okay. So molar solubility, we've got lead 2 chromate. Start with. Means it's get up and go. Yeah, chromate. And it's producing lead 2 plus chromate. Oops, that's dichromate. That's not even dichromate. Need a 7 here for dichromate. There we go. 2 minus this. And this would be KSP would be equal to 2 times 10 minus 16. And then the competing reaction is the formation of the complex ion, right, with thiosulfate. Sodium is a spectator. So we're looking at taking the lead 2 plus, combining it with thiosulfate 2 minus. Say there are 2 sodiums, each with a plus, so that means that thiosulfate has to be 2 minus. And it produces the complex ion. How many of them are there? 3. Yeah. So 3 of these, 3 times 2 is 6 minus, and a 2 plus is a 4 minus. So our charge is balanced. And the formation constant is 2.2 times 10 to the 6th. Okay. Now, what we're given is a concentration of this one. And that's it. What we need is an equation that expresses this entire reaction. So that's why we have to add them together. All right. So I'm going to stretch it out here a little bit. That one plus this one. Probably should have started with the solid. Then we've got 2 plus chromate and the complex ion. what's the KEQ for this? Is the product of those two Ks. 2.16 and 2.2, 6. And this is 4.4 times 10 to the minus 10. All right. We've got lead on both sides, so it goes out. And we're going to base our solubility on the relationship of lead to chromate. Right? Because for every one lead, we have one chromate. So this is going to be our unknown. And tell us what the solubility is. So let's see. Yeah. Okay. So initial change equilibrium. So what are our starting points? We've got 0.055 molar thiosulfate. 0.055 molar thiosulfate. Okay. And with that, we're going to produce, let's see, the ratio here is, oops, this needs to be 3, doesn't it? I should have caught that. All right, so with this amount, if we make this one solubility, actually, initial is 0. We make this one the solubility. Then for each one of these has been used, and 3 of these must be used. All right, so if the change is going to lose some of this, then it's going to lose 3 of these. Right? So 0 point, let's see, not yet, minus 3 S's. So for every one of these, we have to lose 3 of these to make one of these. So this is going to be plus S also. That's kind of stuck in there, sorry. If this starts off at 0, then since this is one lead, one chromate, one lead, one chromate, one lead, then they have to be the same value. Okay? So the only ones that are important for our equilibrium are this one, 0.055 minus 3S, and S and S. Okay? So our equilibrium constant is 4.4 times 10 to the minus 10. And that's equal to the chromate. And instead of writing that up here, that's going to be this one times this one. And since their coefficient is 1, they're going to be S squared in the numerator. And in the denominator, we're going to have this one to the third power. 0.055 minus 3S to the third power because of that coefficient. All right. This one's not as easy to deal with because what we're going to have to say is S a significant part, percentage of 0.055? And if we don't do that, then we're kind of out in the cold. I don't think there's any way around that. If we took the root of this one That would leave us with 2/3 root here, and so that wouldn't work. Not without a supercomputer. So let's estimate this one as s squared over 0.055 cubed. So I cube that one and multiply it times this. 0.055 and cube it. That's 1.66 times 10 to the minus 4 times this value, 4.4 exponent minus 10 times, and that s squared is equal to 7.32 times 10 to the minus 14, and then I just take the square root of that. It's 2.71 times 10 to the minus 7 molar. That's the molar solubility in that system. A. Okay. Now, if we were doing some type of research, we would definitely have to go back and satisfy the 5% rule. But we're assuming that the 5% rule is fine because of such a small value of the EQ. It's going to produce very little S in this term. And we're justified in estimating. Got any more? Is that it? Okay. So,